thank you very much for the introduction. My name is Christopher Pickett-Heaps. Probably a slight change in the title. I thought I'd give a more an overview of hydrological forecasting services across the Bureau to give a bit of context before drilling down into some more technical details around forecast post-processing. Before we get going, I just want to pay acknowledgement to country. So pay my respect to and acknowledge the Ngunnawal people, who are the people of and the custodians of the Canberra region, and pay respect to the custodians of the land in which I meet today. So that's in Canberra, and I pay my respects to their elders past and present. Thank you, particularly because we had I had Reconciliation Day yesterday, which is a public holiday in Canberra. Okay, so just a brief outline of my talk. So I'll give a really brief, so why does the Bureau provide water information and forecast services, particularly because the Bureau is obviously the National Weather Service, to use a general term for Australia, and a little bit of history of why this is the case. Very brief, but a bit of introduction. Just quickly look at the forecast services within the water space at different timescales and the types of hydrological models used to support these services. And then I'll briefly look into catchment-based hydrological forecasting services before looking in more detail, partly because this is what I'm involved in, is nationwide grid-scale hydrological forecasting services. And that's within the Australian Water Outlook, which is a service now operational and provided to the Australian public. And hopefully there'll be time to look at current projects we're involved in, which is unifying a lot of these services under a single operational and modeling systems. Okay, so why do we provide forecast services to Australian community? We all know, and we're very aware of, Australia is significantly impacted by pretty significant climate variability, and that leads to significant variation, interannual variations in water availability, very high variability in stream flow. In addition, the country is the second, well, if you exclude Antarctica, it's the driest continent on Earth. It's a relatively low, I suppose, mean annual rainfall across the country, but it's pretty extraordinary in the degree to which a lot of that rainfall is lost to evaporation, meaning that a relatively small amount or small percentage of that water that falls on the continent every year turns into runoff, and that runoff leads into water in our rivers and dams, and that's how we are able to make use of that water resource, but it is very limited. And as the population has grown, dependency on those water resources has increased substantially. That's led to a significant infrastructure building over the last 50 years, particularly from the after 1950, particularly 1960s, 70s, 80s. A lot of infrastructure was built. I think dams, water management infrastructure, irrigation, or infrastructure supporting irrigation. Unfortunately, during that period, it was actually quite a wet period within Australia, and there's probably was somewhat less knowledge or general knowledge of the variability in which exists over a longer term of the water availability across Australia. And so subsequent to 1990 or leading into 2000, we hit the millennium drought. And we all know that that was a pretty significant stressful time period where Australia's experienced significant stresses on its limited water resources, and it really led to a pretty significant crisis in 2006. I was actually living overseas at the time, where there was basically a crisis in water supply over the Murray-Darling Basin, where guaranteed water supply to Adelaide was actually not assured, partly because there was very significant water resource limitations, coupled with the fact that there was a general lack of knowledge of the amount of water in the Murray-Darling Basin. Adelaide being a city whose water supply is provided by the Murray River. So that led to the Water Act of 2007 that gave legislative backing for the Bureau to provide a bunch of water information services to the Australian public. Now, just to reiterate the impact of climate variability, this chart shows the variation in the amount of water stored in the combined storage levels of the Hume and Dartmouth dams there in the lower Murray-Darling Basin. know many of you perhaps from Sydney, so it might not be so familiar, but Hume River obviously lies on the border between New South Wales and Victoria. It's on the Murray-Darling Basin. Dartmouth is upstream, not on the Murray River, but upstream in the Victorian Alps. This is some pretty important water storage infrastructure for the lower Murray-Darling Basin. And what we see here is the variation from 1981 of the storage capacity. And what you notice, and highlighted in red, is when in the El Nino years, we have periods over more than 1 year of an El Nino event, the annual refill in the winter is significantly reduced. And so the climate variability does have a very direct impact on water availability. In this case, it's shown for these two important water storages in the Upper Murray and shown here in the map. It just underscores the importance of having knowledge about the water resources and potentially predicting the likely changes in those water resources into the future. So water information products from the Bureau, they span multiple timescales. So in the past, we provide historical climate data and historical hydrological data, as well as information about what's happened in the past and what's the current status of water resources more generally, as well as providing foresight. So that's in the form of forecasts. Now, flood forecasting was a very traditional service or long-standing service. It's been provided by the Bureau for decades now, but over the last 15 years, other services have come up. So I'll go into a bit more detail. So as I said, flood forecasting has been provided traditionally, but now we're providing forecasts out to a week of hydrological forecasts, as well as seasonal forecasts and even scenario analyses. So what does this mean? So flood forecasting is analogous to severe weather updates and warnings. And what we call here flow forecasts, so forecasts up to 7 days, are analogous to weather forecasts that we get across the country. And the seasonal outlook is similar and is driven by seasonal climate forecasts, and then scenario analyses are driven by climate projections. So we're looking at forecast information products across many different timescales. Now, the hydrological modeling at the Bureau, we're going to be sort of divided into two categories. These are the underlying modeling techniques. The first is distributed modeling across the nation. So these are grid-based models and using and generating grid-based data sets. They're nationwide. It's a nationwide hydrological model taking in as input nationwide gridded data, climate data primarily, and providing gridded output. We'll go into a bit more detail what that output is. It's a single optimized parameter data set underpinning that hydrological model. Is operated at a 5 square kilometer resolution and takes in the gridded climatology and hydrology data sets. Now, the other type are catchment-based or point-based modeling systems. These are point-based at specific locations. These are models are calibrated locally. They're one-dimensional or possibly semi-distributed, which I won't go into the details of that, but they're not fully spatially distributed models. They're primarily one-dimensional models. And they rely on meteorological and hydrological observations. Now, these are locally calibrated, so in a lot of instances, for the locations to which they're available, they provide very high-quality forecasts. Okay, so I'll briefly look at some of the forecast services underpinning these different types of modeling system or modeling techniques. So catchment-based modeling service, there's two services. There's a 7-day forecast streamflow forecasting service and a seasonal forecast service. These are these are models that are locally calibrated at point locations across the country. The other set of services we have is basically provided by the Australian Water Outlook. And these are the Australian Water Outlook is underpinned by grid-based modeling forecasting. It is a grid-based hydrological forecasting service, so it's nationwide. And this service provides, I'll look into this in a lot more detail, that's why I've got it in bold, historical analyses. There's a product under development to provide a 9-day, every day providing a 9-day forecast across the nation, as well as seasonal forecasts and hydrological projections. And the important thing here, that all of these forecasts are ensemble-based probabilistic forecasts. So they're all probabilistic forecasts. That means that they're providing a range of likely scenarios, so you might say, or a range of outcomes that have equal probability, and generally that range is less than what you expect from a more basic data set like historical climatology. Okay, so just briefly, this is a 7-day ensemble streamflow forecasting service. It was released in June 2020. That was actually the ensemble-based version of this service, the actual deterministic-based version. So that's a deterministic forecast that became operational, I think, 2014. The ensemble-based forecasting service was operational in 2020. And it, like I said, it provides point-based forecast locations across the country. It's updated daily, and it provides forecasts out to 7 days. Now, these are either daily forecasts, and again, I emphasize that they're ensemble-based forecasts, or hourly-based. So you're actually getting at basically what is a hydrograph out to 7 days. And those data, the products are obviously available to the user.
Christopher, can I please have a quick question?
Yeah, sure, go for it.
What is the model that's being used behind this? Is that exponential smoothing or ARIMA, or what's the model that
it's a semi-distributed model, which
Okay.
means that it's a collection of rainfall runoff models, which is GR4H. Similar to GR4J. GR4J is run at a daily timescale. GR4J-H is run at an hourly timescale. So I won't maybe go into the details, or I can at the end. Semi-distributed means that you take a catchment and you divide it into different subcatchments, and the models are all combined to create. There's spatial variation there, but it's not a truly grid-based modeling. Importantly, this model does include routing. So the modeling suite, in addition to GR4H, it also includes a routing model, and it includes error post-processing as a pretty important component.
Yeah.
Right. So that's a good question. Thank you. And we provide information, particularly all these products provide information about forecast evaluation and skill.
Thank you.
Okay, no, that's fine. That's a good question. Now, the next service is a seasonal streamflow forecasting service. I was quite involved with this a few years ago, not so much now, but a few years ago. And this is providing seasonal forecasts at these point locations, so going out to 3 months. So these are volumetric flows for individual months out to 3 months. Importantly, some of these sites are targeted reservoirs around the country. So we're actually providing probabilistic forecasts of natural inflows into these dams. You can see some of the products here, and we're giving, again, like for the lower right-hand corner, you can see it giving a probabilistic update of the likelihood of different scenarios. In this case, high flow, near medium flow, or low flow, whether based on terciles, and then the percentage likelihood has been given as an update from the climatology, and that's the product of the forecast. So just quickly, the modeling methodology we use for this particular type of model is a statistical model. So it's not a hydrological model per se. It's based on multivariate normal distribution in transform space. It takes in the main predictive variables, and the information coming in is incident observed streamflow at these locations, which implies that you have as with the short 7-day forecast, you're reliant on the reliable provision of data, hydrological data, coming in to these forecasting systems in order to generate a forecast. And climate indices are also used, and these generate a probabilistic forecast out to 3 months. So it's not this is not a physically based hydrological model like GR4J would be a model, analogous model you might use in this context. So those are point-based forecasting services that I've described. Now we come to a grid-based modeling and forecasting. So the Australian Water Outlook consists of three primary services: historical analysis, or the record and the current state. I'll explain what that means in a minute. It's updated daily, where the input forcing are daily climate grids at 5-kilometer resolution across the country. Think rainfall, solar radiation, minimax temperature, wind speed across the country. Then we have seasonal forecasts at the grid scale. So these are national forecasts across the grid, across the nation at 5-kilometer resolution out to 3 months. where the input forcing is seasonal climate forecasts, in this case from Axis S2, and it's calibrated to a 5 kilometer resolution. And then we've got hydrological projections, which is a decadal, the service providing decadal estimates of the likely change in water resources up to 2100. And they're being forced by climate projections, or GCM climate projections, with various methods for downscaling and bias correction, post-processing. And all of these services are based on the Australian Water Resource and Assessment Land Surface Model, which is a hydrological model. Basically, the land, so this is the AWRA model, Australian Water Resource and Assessment Model, is a land surface model. Some might call it a soil moisture model. Depends on the context that it's used. These types of models are used not just for hydrology, but of interest in the carbon cycle, because the water cycle and the carbon cycle, think carbon budgets, and are very intimately linked. And also, if you're interested in atmospheric modeling, these models are also important for the radiation balance. And so they're, depending on the context, these types of models have a lot of different uses. In this case, we're using it for hydrological modeling. And so, like I said, it's a land surface model, which is basically modeling the surface water balance across Australia, which is represented by 3 soil layers across the country at 5 kilometer resolution. It takes as input climate forcing, so rainfall, temperature, surface wind, solar radiation. And as output, it's producing, so it's representing the soil, the surface water balance across the country. Those are represented by actual evapotranspiration, soil moisture, and runoff, and some various other variables. I mentioned these because these are primarily the forecast variables. Okay, so this is an example. This is the historical analysis and recent conditions. So this is one tab of this service where it's providing, the user can look at the past variations of the surface water balance as represented by these hydrological variables, of which for this particular service, historical service, there's quite a lot of different variables people can look at. It's providing gridded output as well as time series output. Importantly, it's updated daily, so it's giving you the current situation of the surface water balance, again, as represented by these hydrological variables as of today, or as of yesterday. And it's being driven primarily by analyzed climatology grids. Now, what are those? Those are climatological grids, which are, again, daily. They are generated through various modeling processing from observations across the country. Think meteorological observations of rainfall, temperature, wind speed, and various other variables. So that's a historical analysis that one can look at. If we replace the input forcing from, instead of using climate grids, we use grids from a seasonal climate forecast, a seasonal forecasting climate model. So instead of using observed, we call it observed rainfall or gridded rainfall, we're using a seasonal forecast of rainfall, temperature, solar radiation, surface wind. We can use these as input in the land surface model, and importantly, we're using ensembles, or different ensembles of these input. All right, and we can generate forecast output of, for example, actual evapotranspiration, soil moisture, and runoff. And these are forecast variables of the seasonal timescale, and they're ensemble based, so they're probabilistic forecasts. So if we look at this is an example where we're producing a forecast of root zone soil moisture. So that's the soil moisture in the first meter of soil across the country at a 5 kilometer resolution. But so we can provide a map, and that's actually the 50th percentile of the forecast. So it's basically the median of the forecast. We produce a map, and we can also produce a time series for different regions across the country, either points or these are river regions, but also we do these for state jurisdictions. And you can see here what it describes. You can see the analyzed estimates in the past of what was treated as observed, as in this case is soil moisture, and then the forecast change in soil moisture in the next 3 months. And for this particular region, this is the Dalai River region. It's a basin, the defined basin in the Northern Territory. You can see this is for November, December, January. So you can see this is lead up to the wet season for 2021 leading into 2022. And again, you can see the bar plots there are providing the forecast uncertainty, or the range of likely outcomes. We provide that also in percentile space. So this basically is deseasonalized and standardized across the country, so you can see weather forecasts are particularly indicating above average, in this case above average root zone soil moisture, average conditions, or below average. And this, again, it was taken in 2021, so it's a particularly wet period of time. As we know, we've just coming out of a triple La Nina, so it's been quite wet across the country for the last 3 months. And so that generally the soil moistures have been forecast and have been modeled as above average. And so again, so these maps are about 5 kilo resolution, and we also provide time series products for various regions across the country. Now, in particular, I won't go into the details of this, but we also provide information about the likely skill, forecast skill. So this is available to the public, where they can look at how good is the forecast skill for these products out to 3 months. And these are provided as a map with a pretty intuitive color range, where people can see where forecast skill is good or acceptable, and where it's poor skill or limited skill. Forecast skill is usually always in a lot of what the Bureau products provide, and it's not just in hydrology, but also in climate forecasting space. It's provided as an improvement against a baseline model, which is generally a historical climatology. So when you see, in this case, we're seeing positive skill in green, the forecast has been shown by an analysis of past forecasts as providing improved skill or reduced uncertainty, as well as and reduced bias compared to historical climatology. So it's reducing the uncertainty that you would otherwise have simply by having a historical climatology giving you a static mean and variance of a particular parameter. In this case, root zone soil moisture. But we also provide runoff, and the seasonal forecasting sphere we're providing, so seasonal forecasts of root zone soil moisture, runoff, which eventually ends up in rivers, and actual evapotranspiration. Okay, just briefly, I'll just mention the last part of this service is providing, these are the same idea, but these are projections out to 2100. All right, so these are the projected likely changes and the uncertainty associated with these changes in the surface water balance across Australia, as represented by root zone soil moisture runoff. And with a changing climate, which is being modeled by climate projections, we are providing information about the likely changes in water resources across the country. So in this case, we're looking at changes in runoff across Australia. For a particular scenario, this is an emission scenario, such as scenarios are chosen. And where we're seeing across the country, we see either a decrease in likely runoff as we progress to the end of the century, or possibly increase in runoff. And a lot of effort's been placed into providing some level of uncertainty in these projections. Again, these are being forced by climate projections, so climate models providing climate projections, so-called CMET5 climate projections, with various downscaling and bias correction applied. I won't go into the details of those details, but that's another service that they have. Okay, so just quickly, and I'll pause after this if you want to take any questions. I've got some more slides at the end, but just to give you an indication, I mentioned, if we could just go back quickly, we look at forecast skill. This is just for a particular month. This is at the seasonal time scale. If we just look at all months of the year, there we go. Yep, that's all right. Go back one. All months of the year for the first lead time. So that's the first month of the 3-month forecast in January, February, March, all the way to the end. We generally have pretty good skill that's as represented by green in the first month across the country. And this skill does drop off. So if you think of a forecast, you have the first month, and the second month, and the third month, there's a lead time. So lead time 0, lead time 1, lead time 2. So the first month is generally pretty good, and the skill does drop off with soil moisture in the later months of the forecast, but you do still have positive skill, particularly in the winter, spring months in southeastern Australia, which just coincide with the filling season of some of the major reservoirs across the country. Interestingly, with root zone soil moisture, it's been found that the initial states of the land surface model actually has a pretty big impact on your forecast skill, as opposed to the climate forcing that has to do with root zone soil moisture itself. And just showing you on the bottom, I'm not going to do too much detail, but in blue, it's showing whether the forecast is reliable. And generally they are reliable, except reliable being, I won't go into the details just now because of time, but forecasts are generally reliable and acceptable. And you can see the only places where we have trouble with forecast reliability is in the top end in the dry season, which is not that surprising. With runoff, we see a decrease in skill, but it's not too bad. We still have positive skill in the first month, and in many areas in the second and third month, it's not as good as soil moisture. Interestingly, with runoff, we found, or colleagues have found that it's more impacted by the forecast skill of the seasonal climate forcing, as opposed to the initial states of the hydrological model. So this skill is more impacted by the skill, the forecast skill of the climate input forcing, or the climate model that's driving these forecasts. Okay, so I'll just stop it there if I want to take any questions before what I want to talk to at the end, which was actually a bit more the original topic of my seminar, was looking at forecast integration, forecast system integration. So basically bringing in a single land surface or a single physically based model to support these multiple services provided by the Bureau. But before I go into that, I can stop and take any questions if you like. Okay, so on this topic, so it's actually somewhat of a segue to what we were just discussing. So I'm going to talk about seasonal forecasting system integration. So integrating seasonal land surface forecasting with seasonal streamflow forecasting under a single hydrological model, that being AWRA. And actually in the future, the Bureau will be adopting a new land surface model called JULES. I forget the acronym it stands for. But that's a model being developed internationally. It's international collaboration, but it's certainly not an Australian developed model, whereas AWRA-L was developed in Australia at CSIRO in conjunction with the Bureau. And this is being done not just for the pure purposes of science or improving forecast skill, but also in streamlining system maintenance and development. So the Bureau is primarily in a lot of ways a service provider. It is a research organization, but it's not the only thing. Scientific research is not the only area in which the Bureau operates. A significant amount of resources are placed in system development and maintenance, and service delivery and communication, and obviously people involved in forecasting, either hydrology or in meteorology. Point being is that these systems require a lot of maintenance, a lot of development by skilled software engineers, and they have to be very reliable because they're running every day. And basically, at the moment, we have bespoke or separate modeling systems supporting these two forecasting services. And it's a pretty significant burden maintaining, in this case, two modeling systems, but in actual fact, there's lots of modeling systems in the Bureau that the Bureau has to maintain and improve. And there is now a 10-year strategy in the science strategy of research and development to move to a more unifying modeling system that supports many forecasting services, either in the atmosphere or climate space or in the hydrology space. Unfortunately, unlike meteorological observations across the globe that are provided very reliably to meteorological organizations, hydrological data within the Bureau, within Australia, is not always, the delivery is not always that reliable, and that impacts our service and the efficiency in which, particularly the streamflow forecasting service, can be provided. There's reasons for that. I can mention at the end. Because these are separate, there is the potential for inconsistent forecast output because they are completely separate systems with separate inputs. And one thing is that the current seasonal forecasting service for streamflow is not benefiting, not taking the benefit from seasonal climate forecasting. So what we want to do is integrate these two services to enable these two services to be supported by a single physically based modeling system. This will reduce maintenance burden of separate modeling systems and enable full automation of the forecasting service, and that relieves resources within the Bureau, which are quite strained. And importantly, there's no reliance on real-time hydrological observations, the delivery of which is, for a number of reasons, many of which are outside the Bureau's control, are not reliable, and that delays forecast issuance. So in doing so, we want to ensure that we're getting a similar level of forecast skill compared to the current operational service, ensure consistency between two forecasting services, and allow the seasonal streamflow forecasting service to take advantage of climate, physically based climate forecasts. So basically, we're integrating. So if we start with, again, we saw this before, but we start with a seasonal streamflow forecasting service. It's based on a statistical modeling, mathematical model, but based on multivariate normal distribution. It's basically the underlying statistical model that's used, where your primary inputs are observed incident conditions or observed streamflow at locations across the country. And that provide, under this particular type of model, normal distribution, by fixing your inputs, you're able to define a conditional probability of your outputs, which happen to be your forecast variables of streamflow at 3 months. So we're replacing those inputs instead of incident conditions. We're replacing these with forecast variables and basically input variables from Australian water outlook. So these being recent historical simulations of root zone soil moisture runoff and the equivalent forecast variables out to 3 months of root zone soil moisture and runoff. And I make the point that the key for this to work is the seasonal forecasts of these variables, so root zone soil moisture and runoff from the land surface model, have forecast scale themselves out to 3 months, and that there's a good correlation between these forecast variables and streamflow. And that allows you to make a correction based on the input forecast to generate reliable and skillful forecasts of seasonal streamflow. Now, this, depending on the context, you could treat this as basically this statistical model as an error processing model to generate. If you treat, for example, runoff as an estimate of streamflow, it isn't some would argue it isn't for various reasons. But we can use that as an initial estimate, and we apply an error correction model to generate streamflow forecasts. And we calibrate that in the past. I'll go to that in a minute. Just a bit more specific, so you've got your input variables. So AWRA-L forecast at 3 lead times, so month 0, 1, 2, and 3, as well as the sort of observed conditions in the past, the previous month, very analogous to just using antecedent streamflow observations. And your predicted variables are, as we said previously, as a gauged forecast streamflow out to 3 months. Now, the important part here is the calibration, so model calibration. How do we calibrate this statistical model, which again is a multivariate normal distribution in transform space? So, and just to reiterate, with this particular formulation of the model, both the predictors and predictands are treated as random variables that are very likely correlated in time and space, or in this case, time, mainly time. And so if you fixed the predictive variables, if you fix it to a single value, such as the median of these 4 input forecasts, you can get a conditional probability of the outcome, which is our seasonal streamflow forecast. So to calibrate these models, what do we need? We need the retrospective forecasts. We call them retrospective forecasts or hindcasts, so in the past, from our gridded model from AWRA-L, from AWRA-L. And we do post-processing for various catchments across the country, represented by the gauge locations, as well as historical streamflow at the same locations. And with these two data sets, predictors and predictands, we can calibrate our statistical model. And with that calibration, we can provide a forecast. So in this case, I can just show this timeline from 1981 to 2018. We calibrate the model based on these data, these pairs. And then with that calibrated model, we can provide a forecast in the future, or future being post 2018. And incidentally, these retrospective forecasts from Australian Water Outlook from AWRA-L are the same ones that were used to generate the forecast skill of the seasonal forecasts, the Landsat, the gridded seasonal forecast that I showed previously. So there's a very direct link there. That's confusing. I can come to that again. Just very briefly. So that's fine. That works. But one of the most important things we need to be able to do is demonstrate our forecast skill. And we do that by generating forecasts in the past. In this case, what we want to do is generate past forecasts of streamflow. Within those, we can generate forecast skill metrics, and we can analyze those metrics. Just very quickly, but if we want to do this, it's a bit complicated. If, for example, we want to generate a retrospective forecast for 1990, we have data that we need to calibrate with, but we also need to ensure that our calibrated model is independent of a particular forecast, in this case in 1990, right? This is a retrospective forecast. And so basically we leave out 5 years of data, and that allows us to be confident that the data we're using, historical data that we're using to calibrate our model, is independent of a past forecast that we were generating, okay? And this is true. So for climate forecasting, they generate a hindcast across the country, and they analyze the skill of that climate forecast, and it's available to the public, right? Similarly with Australian Water Outlook, we do the same thing. So it's very common. We generate a hindcast, which is a set of retrospective forecasts, and with that, we can test how good our forecast is, right? So what this implies is, in the hindcast mode, we actually have to run a calibration for every retrospective forecast, basically because the data changes every time. And so this is computationally pretty intensive. Relative to just running a forecast, real-time forecast, the generation of hindcast is quite computationally intensive, has to be done on supercomputers. So just quickly, so the creation of the hindcast data set for forecast verification. You select a year, that's for a particular month, you find your leave-out period, you calibrate the model, you apply the model, you have a retrospective forecast. And for each month of the year, for each site, you generate 37 retrospective forecasts. That's for each month of the year. We just that's a decision to make. We just stratify each month of the year. That's all right. So with these data, these 37 retrospective forecasts, we can calculate monthly skill scores. I won't go into the details of what they are, we don't have time. But the skill scores is a mathematical metric we can use. And we usually do that for historical climatology in a forecast product. And we can use that to assess our forecast skill. How good is our forecast compared to a benchmark model? So with these skill scores, we generate a skill score data set. And from this data set, we can perform a forecast skill analysis, of which, if you're familiar, CRPS is a forecast skill metric, and reliability. Those are the two main ones we use for this current project. And just briefly, so like I said, we stratify calibration data by month. Our hindcast period is 19. So these are the period in which we generate retrospective forecasts. Is from 1981 to 2017. This is directly dictated by the hindcast period of Access S2. So that's the climate forecast, the climate seasonal climate model run by the Bureau. And the equivalent forecasts for those seasonal climate models, seasonal climate forecasts, are available on the Bureau's website. You can have a look at those. And then with the same hindcast we used to generate hindcast using AWRA-L for the hydrological seasonal forecast. And again, it's being driven by this data set. So for a particular site, that implies we have, for each, you have 12 months of the year. So we have 444 total hindcast dates for a single site. For the analysis of forecast skill, that's 481 locations across the country. So it turned out to be quite a computationally intensive exercise, although it's always relative to this. But does have to be completed on HPC. So just briefly, with that, what we find is this on the left side, we find for the first month, on the left side panel shows the number of sites with positive skill. Let's not go into the details of exactly how this is calculated. This is a brief summary, but this is, again, in green is showing the proportion of sites with positive forecast skill, the number of sites with little forecast skill. What that means is the generated forecast isn't particularly bad, but it's not really any different to historical climatology. And then there's some sites that actually produce a worse skill, mainly because of bias. And what we find is with the current situation, we get the current operational service based on antecedent streamflow observations. So we have to have that feed of data coming in across the nation. We can achieve similar forecast skill in the first month with this new mode of operation where we're post-processing forecasts from the Australian Water Outlook. We're generating similar proportions of sites with positive or not forecast skill. And the same is true. This is for lead time 0, so the first month, and we get similar results in lead time 2 and 3. The forecast skills do reduce, so you notice there's quite a lot more proportion of sites that have little forecast skill. Again, it's forecast skill that's not that different to historical climatology. So you're basically generating a product that's similar to historical climatology. And with that, I'll leave it there. I can take some questions. Thank you.